Well, now we know the equations for how to find the equivalent capacitance for any number of capacitors connected in series and any number of capacitors connected in parallel. Let's review those equations really quickly. We'll say C subscript P as a way of saying the equivalent capacitance for capacitors in parallel. This is just equal to C1 plus C2 plus C3, and we can just draw in some ellipses, and for any number of capacitors connected in series. So we'll say 1 over Cs is 1 over C1 plus 1 over C2 plus 1 over C3, and so on. However, these are not the only two options. You don't have to connect all your capacitors strictly in parallel or strictly in series. In fact, you can make some sort of combination. The combination in this diagram here would be described like this. Capacitors 1 and 2 are connected in series, and that series connection in turn is connected in parallel with capacitor number 3. We could think of not just one equivalent circuit for this, but we could imagine reducing it until it appears to be one equivalent circuit. Let me illustrate what I mean by that. We'll shrink this down just to make some room. I believe this circuit would behave in the same way if we left capacitor number 3 alone and then replace capacitors number 1 and 2 with the equivalent capacitance of just those two capacitors according to the formula for capacitors in series. Then we can take these values and imagine reducing it down to some equivalent circuit once again, so that the total equivalent capacitance would be nothing more than C3 plus the equivalent value of C1 and 2 in series, right? Capacitors 1 and 2 are in series, and then that is in turn in parallel with capacitor number 3. Okay, maybe more interestingly, how would we make this connection? If we call this capacitor 1, and this one number 2, and this one number 3, how would you connect the wires from this battery to make it such that capacitors 1 and 2 are in series, and then that in turn is in parallel with 3? Well, if you'd like to, I recommend you hit pause on this video and either with your fingers actually trace the screen of your computer and imagine what those wires would look like, or better yet, hit pause and sketch out a picture that looks like this and see if you can figure out how you would do the wiring. Okay, so now that you've made your own guess, let me show you if you've got it right. We go from the positive terminal to capacitor number 1, from the negative terminal to capacitor number 2, and then those two are connected together. Let me make this clear by getting rid of this circle. Or, there's an alternative. We could connect from the positive terminal of capacitor number 3 to the positive terminal of the battery, and from the negative terminal of capacitor number 3 to the negative terminal of the battery. Yeah, that's the circuit diagram that matches this one. Now, what language would you use to describe this combination? There's capacitor 1, 2, and 3. Would you say that capacitor number 1 is in parallel with or in series with capacitor number 2? Is capacitor number 1 in parallel with or in series with capacitor number 2? Well, actually the answer is neither. Capacitor number 1 is neither in series nor in parallel with capacitor number 2. I know this for sure. Capacitor number 2 is in parallel with capacitor number 3, and I can think of that as having some equivalent capacitance that we'll call C23. Whatever that happens to be, it's in series with capacitor number 1. So in the end, we could reduce this down to some single equivalent capacitance. how would you actually connect it? What would you do with the wires to make capacitor number 1 in series with the parallel combination of capacitors 2 and 3? So once again, press pause, draw out your own diagram, and resume play when you think you have it figured out. Okay, so let's start by putting 2 and 3 together in parallel. That means that the positive terminal of 2 and the positive terminal of 3 have to be connected together, and the negative terminal of 2 and the negative terminal of 3 have to be connected together. So we can see in the circuit diagram the positive terminal of the battery makes a connection to one part of capacitor number 1. So we'll go from the positive terminal of the battery into the positive terminal of capacitor number 1. Now, where does the negative terminal of the battery go to? Well, it goes to both 2 and 3, that wire junction somewhere. So we can take a wire from the negative terminal, and how about we just imagine connecting it there in a junction. Okay? Now, where does the other plate of capacitor number 1 go to? It creates another junction in the circuit, and it goes off to 2 and to 3. So we can come from the negative terminal of capacitor number 1 and create a junction that goes off to capacitors 2 and 3. So that's how you might actually wire this circuit together. Now, as an alternative, it would be the same thing to make this connection, and likewise, instead of putting a junction in the wires, you could connect like this. So I'll let you think about that and convince yourself that that's still the same circuit. Okay. Let's make an example problem out of this. Let's say we have these 3 capacitors, C1, C2, and C3. So the language here is capacitors 2 and 3 are connected in series, and that series connection is in parallel with capacitor number 1. And what we'd like to figure out is how much energy is stored in capacitor number 3. Well, the trick to this, if you can figure out what the potential difference is, what's the voltage of any individual given capacitor, then you should be able to find its energy, right? After all, energy in a capacitor is either 1/2 CV squared, 1/2 QV, or Q squared over 2C. So we'll always know what the values of C are. They should be given in the problem. So like I say, as long as you know the potential difference for that given capacitor, then you know how much energy is stored. And likewise, if you know both the capacitance and the potential difference, then you know how much charge is stored on that capacitor. So that's the trick, is finding the individual potential differences. Now, what's the voltage applied to the 12 millifarad capacitor? Well, some would say, the voltage applied, it's as clear as day. It's 20 volts. No, that's the voltage applied to the whole circuit. The electric potential at all the points in the circuit indicated in blue would be 0 volts. And the electric potential at any point indicated in red would be 20 volts. So what's the potential difference? What's the voltage for capacitor number 1? Well, we can see 20 and 0. So let's write in the values of capacitance in this chart. This might be a convenient way to solve this problem. So we have one capacitor that's 6 millifarads. We've got a second capacitor that's 4 millifarads and a third capacitor that's 12 millifarads. Now we also want the equivalent capacitance. Okay, well, we figured out this much. The voltage across capacitor number 1 is the full 20 volts. However, the electric potential here at point A is 20 volts, and the electric potential here at point C is 0 volts. but we don't know the electric potential at point B, so we don't know the voltage across either capacitor 2 or capacitor number 3. Not a problem. Let's draw the reduced circuit diagram like this. So we've got the full 20 volts. We still have our capacitor number 1, which is 6 millifarads, and then this is the equivalent capacitance of 2 and 3. Now those two are connected in series, so let's use the equation for series. Since there's only 2 of them, we can use the simplified version. Instead of saying 1 over C equivalent is 1 over C1 plus 1 over C2, we can say C equivalent is C1 times C2 over C1 plus C2. So this is 4 times 12, 48, over 4 plus 12, 16, which gives us 3. So C1 is 6 millifarads, and the equivalent capacitance of C2 and 3 in series is 3 millifarads. Now, if we want to simplify it yet again, we can say this just acts like one single capacitor, CEQ, and because these two are in parallel, it's very easy. This is 9 millifarads. Okay. So when we apply 20 volts to an equivalent capacitance of 9 millifarads, then what's the amount of charge that develops? Well, let's look at our special triangle, QCV. So when we cover up charge, we find it by multiplying capacitance times voltage. So 20 times 9 gives us 180 millicoulombs. By the way, 20 times 6 gives us 120 millicoulombs. In other words, the magnitude of charge on this plate is equal to positive 180 millicoulombs. The magnitude of charge is also 180 here, but it's negative. So the total charge, of course, is 0. Now, if we trace that idea back to this picture, where are those 180 millicoulombs? Well, some of them are here on capacitor number 1, and some of them are here spread out across the top plate of capacitor number 2 and the bottom plate of capacitor number 3. The top plate of capacitor number 2 and the bottom plate of capacitor number 3. But we know how much of that 180 millicoulombs is on this 6 millifarad, because we solved for that working across this row using the equation. So if there's 120 millicoulombs here, then we must be left with 60 millicoulombs here to add up to our 180. So this charge is equal to 60 millicoulombs. And because the 4 millifarad and 12 millifarad are connected in series, charge by polarization takes place. And so the amount of charge on both of those capacitors must be the same. So these are both 60 millicoulombs of charge. The equation holds true as long as we just work across a single row and don't mix and match. So if we want to solve for voltage, we divide charge by capacitance. So if we divide 60 millicoulombs by 4 millifarads, we get 15 volts. Likewise, if we divide 60 millicoulombs by 12 millifarads, we get 5 volts. Okay, so what's that telling us to say the potential difference across the 4 millifarad capacitor is 15 volts? Remember, the electric potential right here is 20 volts. So if the lower plate is 15 volts lower, then the electric potential here at point B must be 5 volts. And by the way, that means the potential difference across capacitor number 3 is 5 volts minus 0 volts, but we already showed that. It's 5 volts, so everything seems to be working out. Now, which equation do you want to use to find the energy on any given one of these capacitors? Well, at this point, you could use any of the 3 equations because we know all of the values across each row. Okay? So I'll leave it up to you to grab a calculator and show that you can find the energy on capacitor number 1 using all 3 of these equations and get the same result. And you can also find how much total energy is stored in this whole network by working just across this row and using any one of these equations. And I would say don't just use any one of the equations, use all three of them to convince yourself that they all give the same result. In fact, if they don't, that's a sure giveaway that you might have made a mistake when solving problems like this. And we can carry this on to even more complex circuits. We can take a 24-volt battery and connect it to this network of 1, 2, 3, 4, 5 different capacitors. In fact, I think we'll do this in the next video lesson. For now,